In this session, we will talk about drift velocity of current electricity. So we will define it first of all. Current density at any point inside a conductor is defined as the amount of charge flowing per second through a unit area held normal to the direction of the flow of charge at that point. It means that the current density can be found out by dividing the total intensity or magnitude of current by the total area through which the current is flowing off. The current density is denoted by J, and this current density will be equivalent to delta I upon delta A, where delta I is the change in current and delta A is the change in area. For non-uniform area, it can be also expressed as I equals integral J into dA or integral J dA cos theta. Now the next topic is drift velocity. It is defined as the average velocity with which the free electrons move towards the positive end of the conductor under the influence of an external electric field. See, we are talking about this free electrons. You should know that if free electrons are present, then there will be the conduction of electricity in any conductor. Now we are talking about this free electrons, and one more thing is there, external electric field. It means that for doing some work, external agency is required. Here external agency is electric field, and in the terms of this electric field, free electrons will move toward the positive end of the conductor. Mathematically, it can be derived by the formula of acceleration, where A equals Vd upon t, means acceleration is equal to velocity upon time. As you know from the second law of Newton that acceleration is equal to force upon mass. Acceleration is equal to force upon mass, and here this force can be induced into small e into capital E from the formula of electric field. Now putting the value of Vd from the above equation, you can have the formula of drift velocity. As free electrons move in a conductor, so they continuously collides with each other with positive ions. Hence, the time interval between two successive collisions of electrons with the positive ions in the metallic lattice is defined as relaxation time. It is denoted by tau. It is equivalent to mean free path divided by RMS velocity of electrons, means lambda upon VRMS. Now we are going to discuss about the combination of resistances. There are two types of combinations of resistances, that is series and parallel combination. But apart from this, by the combination of these two in a single way, we can have a mixed combination also. In such type of combinations, a single circuit contains both types of combinations, means series and parallel. In series combinations, resistances are connected end to end, that is, second end of first resistor is connected to the first end of the second resistor, and so on. You can see in the figure the types of combination which is in series. Same current flows through each resistance, but potential difference distributes in the ratio of their resistances, that is, the potential difference is directly proportional to the resistance. So the total potential drop is equal to the sum of potential applied across the combination, means the equivalent resistance is denoted by Req is equal to R1 plus R2 plus R3 plus R4 and so on. In parallel combination, the first end of all resistors are connected to one point and second ends of all resistors are connected to other point, means same potential difference appears across each resistance, but current distributes in the ratio of their resistance, that is, the current is inversely proportional to the resistance. Now by seeing a figure, we will clarify that whether the figure contains series combination or parallel combination. In the first case, you will observe that the resistor R1 R2, R3 and R4 are there. These R1, R2 and R3, R4 resistors are connected in series because the second end of first resistor is connected to the first end of second resistor, and the second resistor is connected to the third end of the resistor. Now in the second case, first end of all resistors are connected to one point and second ends of all resistors are connected to the other point. Hence we can say that the second figure is having parallel combinations. An electric cell is a source of energy that maintains a continuous flow of charge in a circuit. Electric cell changes the chemical energy into electrical energy. The next concept is electromotive force. Electric cell has to do some work in maintaining the current through a circuit. The work done by the cell in moving unit positive charge through the whole circuit is called the electromotive force of the cell. Simply we can say that when the cell is kept at the shop of the vendor, then it is known as electromotive force, and if the cell is switched in any electrical appliance, then it is known as electric potential. Thus we can compare the electromotive force and potential difference for an open and closed circuit as follow. Now it is time to define and to know about internal resistance. Internal resistance of a cell is defined as the resistance offered by the electrolyte of the cell to the flow of current through it. It is denoted by small r. Now we can say that resistances are of two types. The first one is internal resistance and the second one is external resistance. The external resistance was termed as resistors. The SI unit of these two resistances are same as ohm. Resistance is a measure of the opposition offered to the current flowing in an electric circuit. Internal resistance of a cell depends on the following factors. It is directly proportional to the separation between the two plates of the cell. It is inversely proportional to the plate's area dipped into the electrolyte. It also depends on the nature, concentration and temperature of the electrolyte and increases with increase in concentration. Similarly, we can talk about external resistance or resistor. On the same basis, the resistance depends on the following factors. It is directly proportional to the length of the conductor. Similarly, it is also directly proportional to the nature of the conductor, temperature, and is inversely proportional to the cross-sectional area of the conductor. The next topic is resistivity. The electrical resistance offered by a substance of unit length and unit cross-sectional area is called resistivity. Resistivity is the intrinsic property of the substance. It is independent of shape and size of the body and is depends upon the nature of the material. It is also known as specific resistance. Now we are going to start a new topic, which is electrical energy. It is defined as the total amount of work done by the source of EMF in maintaining the electric current in the given circuit for a specific time t. As it is very certain that in doing some work energy is required. So while bringing a unit positive charge from infinity to a point or from one point to another point, energy is required and that energy will be consumed in the form of work done. So we can deduce a formula for the work done from potential. Since I means electric current is equal to charge upon time, hence that I can be put in the term of work done, means work done is equal to VIT, and then after we can have two more formula. Now based on this electrical energy, we can also define electric power or electrical power. It is defined as the rate of electrical energy supplied per unit time to maintain flow of electric current through a conductor. So we can say that power is the rate of using energy. We can have the formula of power as work done upon time, and this work done is stored in the form of energy transfer. So we can say that the power is also energy transfer per unit time. It is also equivalent to electrical energy per unit time. The SI unit of power is watt, the SI unit of work done is joule, and the SI unit of electrical energy is also joule. Time, which is very familiar, its SI unit is second. So you can say that power is equal to W by T or E by T. So you have the three formulas and you have the SI unit of each one on the figure. Now the next concept is heating effect of electric current. An electric current through a resistor increases its thermal energy. It means that if the current is passed through highly resistive circuit, then heating effect is generated. Also, these are other situations in which an electric current can produce or absorb thermal energy. Hence, totally this effect is known as heating effect of electric current. Mathematically, we can derive an expression for the energy which is dissipated from the heating effect of electric current by the using of Ohm's law as follow in the figure. Finally, you will have the formula of energy is equal to I square RT. It can be also termed in the term of VIT. The heating effect of electric current is also known as Joule's law of heating. Now we are going to deal with applications of heating effect of current, means the electrical appliances that we are using in our daily life that works on heating effect of electric current. In the same sequence, the first example comes for the electric bulb. In an electric bulb, the filament of bulb gives light because of heating effect of electricity. The filament of bulb is generally made of tungsten metal having melting point equal to 3380 degree Celsius. The next example is electric iron. The element of electric iron is made of alloys having high melting point. Electric heater and geyser work on the same mechanism because the resistivity or electrical resistance is much higher, and when current passes through this higher resistive circuit or current, then it is producing a heating effect, which in turn we are studying in electric iron. The next application is fuse wire. The fuse wire is made of tin lead alloy since it should have low melting point and high resistivity. It is used in series as a safety device in an electric circuit and is designed so as to melt and thereby open the circuit if the current exceeds a predetermined value due to some fault. In simple word, electric fuse is used to protect the electric appliances from high voltage. Now we are going to study about measuring instruments for current and voltage. In this regard, there are various instruments like galvanometer, ammeter and voltmeter which can be used to detect current and voltage depending on the range. But apart from this, we will discuss about two bridges, which is Wheatstone bridge and meter bridge, which will help to understand the relation between current and resistance and other potential also. In this regard, firstly we will deal with galvanometer. It is an instrument used to detect small current passing through it by showing deflection. It does not measure the current. Means one another instrument is there, ammeter, which we will study later, that simplifies or indicates the magnitude or intensity of the current. But galvanometer is only an instrument used to detect small current passing through it by showing deflection. Once again I am repeating, it does not measure current. It can be converted into voltmeter and ammeter also. This galvanometer can be converted into voltmeter and ammeter also. Now first of all we will deal with ammeter. Ammeter as an instrument used to measure current and is always connected in series with the element through which current is to be measured. Small the resistance of a ammeter, more accurate will be its reading, and it will not to change the circuit current. An ammeter is said to be ideal if its resistance R is 0. A galvanometer can be converted into an ammeter by connecting a low resistance, which is called shunt, in parallel to the galvanometer of resistance. Once again, I'm repeating, shunt is a small resistance or very low resistance. We will see the derivational term of this shunt and galvanometer in the classroom time. The next topic is voltmeter. Voltmeter is a device used to measure potential difference and is always connected in parallel with the circuit element across which potential difference is to be measured. Greater the resistance of voltmeter, more accurate will be the reading, as only a small amount of current pass through it by not changing the circuit current. A voltmeter is said to be ideal if its resistance is infinite. A galvanometer can be converted into voltmeter by connecting a large resistance in series with the galvanometer. The next concept is Wheatstone bridge. It is an arrangement of four resistances used to measure one of them in terms of the other. Two upward and downward bridges are formed. That's why it is known as Wheatstone bridge. The bridge is said to be balanced when Ra upon Rx is equal to R1 upon R2. The next topic is meter bridge. A meter bridge is sliding wire bridge or Carey-Foster bridge. It is an instrument work on the principle of just Wheatstone bridge. The potentiometer is an instrument that can be used to measure the EMF or the internal resistance of an unknown source. It is a device which does not draw any current through the circuit to measure the potential difference. Hence, it is equivalent to an ideal voltmeter. It has a number of applications.